to particle physics.
Thank you very much. I would like to thank, first of all, the organizer for giving me this opportunity to join this very nice conference. Yes, I'm Federica Pompa. I'm a PhD at University of Valencia. I'm actually finishing. And today I'm going to give you an idea of the work I've done so far with my PhD. And I'm going to give you an overview of the future landscape, of the future perspective for neutrino mass measurement. Well, starting from the description that standard model gives us of neutrinos, we know that in the standard model, neutrinos are weakly interacting particles appearing in 3 different flavors with 0 electron charge and, of course, 0 masses. Nowadays, all of us know that the description that the standard model provided about neutrinos is not actually the correct one, because we know that neutrinos cannot be massless. They must have small, but not 0 masses. The confirmation of the smallest non-neutrino masses came from the observation of the neutrino flavor oscillations, which basically has been recently discovered. And also this discovery has been awarded with a Nobel Prize. And for those of you that was present last week at the school, we had the opportunity to have Kajita with us, and it was a very huge honor for us to attend his lectures. So the discovery of these neutrino flavor oscillations confirmed the fact that neutrino must have non-zero masses. From this moment on, several experiments ranging from cosmology to particle and astroparticle physics are trying to measure this neutrino mass, which is basically, it's very hard to measure. I'm going to focus on 2 different methods that allows, I'm so sorry, can you see? Okay, no, because it's a bit dark, but I'm going to focus on these 2 different methods, which are basically the measure of the time delay that massive neutrino acquired during the propagation, which actually has been already studied by Francesco Bassani, and which put this upper bound on neutrino masses. And also, I'm going to focus also on the possibility that neutrinoless double beta decay searches gives us in terms of neutrino mass constraints. So let's start with collapse supernovae. Why core collapse supernovae are important? Well, first of all, because have been already observed. We have already observed the neutrino signal coming from a supernova explosion, the supernova 1987A. And many neutrino properties have been already constrained with this signal. So we know that it is possible to perform neutrino physics with supernovae. Secondly, because, of course, supernovae are neutrino factories. Almost 99% of the energy released by the explosion is emitted by neutrinos and antineutrinos of MEV of all flavors. And of course, these astrophysical events are very important also because allow to perform a kind of astrophysical physics. In fact, in this environment, these are possible environments in which cosmic rays have been accelerated, which is another open question of astrophysics, and also for the production of light and heaviest element to study the composition of the universe. And as final point, they represent also, let's say, a cosmic laboratories in which interaction of fundamental particles can be studied at the energies which that basically cannot be reached by human-made laboratories, and in which basically new physics may be present. The negative aspect of doing physics with supernova is that we do not have any control where nor when the next one will occur. This sketch, you can see basically, this is a schematic view which basically represents the distribution of the core collapse supernova in our universe as a function of the distance to the Earth. And basically, with the technology that we have, that we currently have, and that we will have in the near future, we will be able also to observe core collapse supernovae nearby, so within our galaxies or to near galaxies, and we could be actually very close to the next observation. When we have to study, when we have to deal with supernovae, we have to rely on supernova simulations. This is basically the way in which the neutrino emission from a supernova can be basically factorized in three main phases. We have the neutronization burst, which so the upper panel is basically the luminosity of supernova neutrino full of flavors extracted by simulation from the Garching modeling group, while the bottom one is the mean energy distribution as a function of time. So the first phase is the so-called neutronization burst, which is characterized by this sharp peak which is present in the electronic component of the supernova neutrino flux. And this is an important phase because I'm going to explain you why later on. And then we have the accretion phase as the cooling one. And the whole emission, or the whole supernova neutrino emission, lasts for about 10 seconds. When we have to estimate the interaction rate at the detector, we have to take into account both the detector features and also the feature of the interaction channels, but also the feature of the source and then all the propagation effects. In this, the results that I'm going to present now focuses basically on two main future supernova neutrino observatory, which are which will be basically sensitive to the electronic component of the supernova neutrino via charge current interaction with argon nuclei, and also the hypercameo, which will be mainly sensitive to electron antineutrinos via beta decay interaction, but is also sensitive to all other non-electronic flavor neutrinos via elastic scattering one. So the effect of the neutrino mass can be implemented as a time delay, which is an energy-dependent time delay effect, which basically neutrino acquired during the propagation to the detector. The effect of this time delay is basically to produce a distortion of the expected distribution of the neutrino at the detector, and as you can see, this energy-dependent makes that more energetic neutrinos acquire smaller delays and then arrive at the detector first. Once implemented into this time delay into the analysis, these are the results that we got in terms of upper bound on neutrino masses with the Dune detector. We are assuming the 10 kiloparsec supernova distance as the basically benchmark. And on this left side, you can see basically the expected rate at the detector as a function of time with this zoom in the neutronization peak time window, in which you can see basically you can recognize a peak hierarchy. The blue one is the non-oscillation case, which I have reported just for comparison reason, and the green one is the inverted ordering case, while the red one, in which the neutronization peak is completely absent or strongly suppressed, is the normal ordering case. Well, I'm going to this peak hierarchy. You can see that reflects basically the result, the upper bounds that we found for the from two different progenitors. We assume just to compare the overall effect. And what we can see from the comparison of these two results is that basically the case in which the neutronization peak is present, so the non-oscillation case, but in particular the inverted ordering one, the results are basically consistent between different progenitors. While in the cases in which the nucleation peak is suppressed, have access to this sharp time. The bounds we got are extreme, gets worse because the fact that in this case we cannot measure the peak, but we have to rely on the whole statistic collected by the whole explosion. And of course, in the cases in which the statistics, the expected statistics, the expected statistics is here, in this case, in the higher mass progenitor 1, the bounds are better. We repeated also analysis with the hyper K, in which if you include the gadolinium hypothesis, you in principle are able to discriminate the inverse beta decay to the other channels, and you can treat these two channels as independent channels, and then you can basically perform the statistic analysis separate, and then combining the two. And you can see that basically the importance of detecting the neutralization peak in hyper via elastic scattering channel, because it can a small improvement of the result. So moving from an basically mass ordering independent upper bound to a mass ordering dependent one, because we have now access to the peak. So we have access to the electronic component of the flux. I'm going to move to the last part, the one related to neutrinoless double beta decay. So neutrinoless double beta decay is an hypothetical nuclear transition in which two neutrons in the same nucleus undergo beta decay, electron in the final state, but no neutrinos. And for this reason, this decay cannot be described by the standard model because it violates lepton number by 2 units. So it has been described in terms of a more complex and more general effective field theory, BSM physics. And today it represents the only feasible way we have to prove the Majorana nature of neutrino. The decay amplitude of neutrinoless double beta decay can be factorized basically in three main terms, which are basically the phase space factor, which it's related to the kinematic of the decay, the nuclear matrix element, which describes the nuclear structure of the initial and the final nuclei, and also, of course, is dependent to the different lepton number violating model we used to describe this transition. Of course, you can basically formulate it a lot of lepton number violating model leading to neutrinoless double beta decay. But the most studied and well-justified one is the so-called light Majorana neutrino model, which is basically when the decay is mediated by the exchange of light Majorana neutrinos. And in this case, parameter that describes this, the operator that describes this model is the so-called effective Majorana mass, which is basically related to the neutrino mass ordering and to the neutrino mass. And this is why it is directly connected to neutrino mass ordering and to neutrino mass. And this is why it is one of the most well-motivated and studied one. The problematic of this study is, besides the complexity of the effective field theory behind, also especially to the description of the nuclear part of the decay. In this table, I'm reporting basically the calculation that have been made for the nuclear matrix element in the, of course, light Majorana neutrino exchange scenario, performed basically by different nuclear model assumption. And you can see that basically assuming a nuclear model, there are several independent simulation groups that are performing the calculation, and that still disagrees on the final result of this nuclear matrix element. And also you can see that there are a lot of missing pieces in this table. So this can give you an idea of the complexity and the huge uncertainty that still affect this topic, this nuclear topic. And also, recently has been pointed out the existence, beside this long-range part to the decay amplitude, to another term, the so-called short-range interaction. Thank you. Which basically is can be, of course, parameterized in this case in the nuclear matrix part of the decay amplitude. And for this, there are still huge uncertainties on both the absolute value and also on the sign. Even if there is, it seems that there are some hints that for its sign to be positive, this is a basically positive aspect, because it means that its contribution will enhance the expected decay rate amplitude. But yes, there are still a lot of uncertainty also on this part. These are the results. These are the basically current sensitivity, current bounds on the effective Majorana mass that we have, exploiting basically the current experiment, the current neutrinoless double beta decay experiment. And in this case, I introduced both the possibility for the short range to be positive or negative. And basically, you can see that besides the huge uncertainties, the huge uncertainty carried by the unknown sign and absolute value of this contribution, you can see basically that there are some, in some cases, we are already touching the upper bound on the inverted mass ordering region. And more promising is the future landscape, in which basically we are expecting to build this very powerful next generation experiment, which basically can lead to a completely can lead us to completely explore the inverted mass ordering region. And also, the problem here is always related to the nuclear physics part, because to the nuclear physics part, both for the long term and the short one, as you can see here. And also, since there are a lot of missing pieces in the nuclear matrix element calculation, we have to find a way to unify the two global picture. Basically, these are basically the results, which here I'm also including the contribution of the molybdenum, which is one of the most problematic one, because is calculation are completely absent for both short and long range matrix element calculation. So, but the picture seems to be promising case in which the leading lepton number violating contribution comes from the light Majorana neutrino exchange. This brings me to my conclusions. I convinced you to the importance of future detection of the neutronization peak, the neutronization burst, for the next generation of detector, in order to put constraints on these on the neutrino mass, which are basically model independent, since it results to be a boost description of the supernova model, and also complementary to the cosmology and laboratory searches. Also, on the neutrinoless double beta decay side, there are the future landscape is very promising, but there are still a lot of missing pieces, especially from the nuclear model, nuclear theory side. So what we can do, we have to be prepared and wait for the next supernova to occur. And of course, we have to necessarily wait for additional hints from nuclear physics. Thank you very much.
Thank you, Federica,
Thank you.
for the nice talk. We have time for questions.
I have a comment and a question. The comment is, you mentioned the work by Pagliaroli on the first part. You talked about the mass measurements with the time time of flight using supernova 97A. But I just want to mention that this kind of analysis was, but not for supernova 97A, but for supernova was already discussed in 1999 by
Yeah, you're right.
Vogel and Physical Review D.
You're right.
I think that was the first.
Yeah. Thank you.
And the second, it's unclear to me. So this short range correlations, I mean, are usually consistently calculated in each model. So what did you do exactly? I mean, usually this contribution is consistently calculated in a given model.
I didn't calculate this. These are numbers that.
No, this I know you didn't.
Okay.
I mean, I know these models very well.
Okay.
So I would like to understand what was your contribution on this part exactly? I mean, this short.
So basically, yes, the contribution was to estimate. Basically, I'm not sure for the current picture, but at least for the future landscape, to evaluate how the uncertainties on both the absolute value and of course on the sign, because you can see basically, yes, and just a contribution in terms of future projection of sensitivity to the effect in Majorana mass. In the, of course, light Majorana neutrino exchange scenario.
Okay, thank you.
If you want, we can discuss later, probably.
A question. So in the limit for the mass, you show an uncertainty. This is statistical or is also
It's statistical.
Or is statistical? Yeah. So we estimated the theoretical one should not be very large, but one should
not
find a way of somehow including it. It's not that trivial.
Yeah.
You rely on a somehow model calculated and given without errors.
Yeah. Yes. Okay. No, yeah. In this case, I'm only showing the statistical one, but okay. Thank you.
You go to the limits on neutrino mass from time of flight for hypercane?
This one?
So, yeah. So just looking at this and comparing to like existing Contran limits, another way of interpreting this plot is saying it's very unlikely that we will learn the absolute neutrino mass from a supernova neutrino burst in our galaxy,
Yeah.
right? Yeah. This is not something, if the answer is that's correct.
Yeah.
Then that's really interesting. And now
Yeah.
the answer to that when I'm asked by other people.
This is interesting. So we also contributed, like Federica, with some calculation that generally agree with what you said is fair. Also, probably one should say that these limits rely a lot on the first event. So this is even more hectic in a sense, because I mean, depending, and however, somehow what you obtain precisely does depend when this event arrives, which energy it has, whether you know the burst from, say, independent ways, like from gravitational burst, if it is in the beginning, whether you have this neutronization peak. I mean, this is indeed the message is not very somehow, I mean, comforting, I would say. Yeah. However, what you will get exactly will depend upon what you will be able to patch up during this situation. Yeah.
Exactly, because this is, of course, a very complicated environment, so we cannot do much with this, but yes, I agree with
For your current, as we know, the recent DESIS result gives an lower bound on the neutrino mass is 0.0.
which bound? Sorry, I cannot hear you very well. Sorry.
The DESIS.
DESI, yes.
Yeah, 0.072 is which is obviously lower than the particle physics bound. It is smaller than the 0.1 if you know. So I just want to know what do the particle physics community think of this lower bound, it seems that there is a tension between the cosmological observations and particle physics oscillation experiments, you know. So I just want to know what do you think?
I have to think about this because now I cannot answer. I don't know how. But thank you. If you want, we can
Yeah,
discuss later.
Yeah, I think that's very important, and it's a very new progress on the neutrino masses. I think the
Yeah.
cosmology community and the particle physics community must consider this point.
Yeah, sure.
This bounding is
Yeah,
very.
yeah, yeah. Mm-hmm.
Well, I think Maria already showed that this bound is with a prior that the mass is bigger than 0. If you show the prior that it should be bigger than the smallest value from oscillation, the limit is not that one. It's around 0.1, 0.11 as far as I remember.
I have to say that I'm not an expert of cosmology, Daisy, or so that's the reason why I cannot comment you more. But yeah, probably with the other discussion we had.
Instead of like concave supernova, why don't you like consider diffusion supernova background?
Okay, for the diffuse supernova neutrino background, there are some perspective in the future. I don't remember now well, but yeah, with hyper K and I don't remember, but yeah. Mm.
Yeah, but you don't know.
Yeah.
We completely prepared.
I was wondering if you've done a combination between Hyper K and Dune to see how much that helps. And also, I think Dune also has elastic scatters as well, which I don't know if it's important to know the direction of the supernova for these constraints, but that could help you potentially.
We didn't perform the combination between the two detectors. And regarding this elastic scattering in Dune, I don't know if it could in some way improve the bounds, but in any case, the one that of course will reach hyper K will be better. So I don't know how they detect the directionality of the flux will help. But I don't know, because this is something that I never thought about. But thank you for the comment.
Other questions or comments? If not, let us thank again.